Vector database is one of those phrases that keeps showing up everywhere right now. You hear it in AI tutorials, in product launches, in job listings, and most of the time the person saying it either moves past it too fast or wraps it in so much technical language that you end up more confused than before you started. But here is the honest thing about vector databases. Once someone actually shows you what the pieces are and why they exist, it stops being intimidating and starts being obvious. That is what this video is. No vendor pitch, no framework wars, no you absolutely need this right now energy. Just a clear explanation of what a vector database actually is, when it is useful, and when you are better off not reaching for one at all. Before you can understand a vector database, you need to understand what it stores. And what it stores is called an embedding. So let me explain that first, because everything else hangs on it. An embedding is a way of turning a piece of text into a list of numbers. A long list, usually hundreds or even thousands of numbers long. The key thing is that those numbers are not random. They're produced by a model that has learned, from a huge amount of text, what words and sentences tend to mean in relation to each other. So the numbers capture something about the meaning of the text, not perfectly, not literally, but usefully. A sentence about a dog and a sentence about a puppy will produce lists of numbers that are close to each other. A sentence about a dog and a sentence about compound interest will produce lists that are far apart. The distance between the lists reflects something real about how related the ideas are. That is the whole trick. You turn language into numbers and then you can do math on meaning. You might be wondering why they call these lists vectors instead of just lists of numbers. The word vector comes from linear algebra, which is a branch of mathematics that deals with lists of numbers and how to compute with them. A vector is just an ordered list of numbers with a defined length. When people say a model produces a 1536-dimensional vector, they mean a list of 1536 numbers. That is it. There is nothing exotic happening here. The reason the field uses this word is that the same math used in geometry to measure distances and angles between arrows in space works perfectly well on these lists. You can calculate how similar two embeddings are by measuring the angle or the distance between them as if they were arrows pointing in different space. The math is old and well understood. The application to text meaning is what is new and useful. So what does a vector database actually do? Now that you know what an embedding is, a vector database is almost self-explanatory. It is a system that stores embeddings and lets you search through them by similarity. You give it a query, it turns that query into an embedding the same way, and then it finds the stored embeddings that are closest to your query in that mathematical sense. Closest meaning most similar in meaning, not most similar in exact words. This is different from a normal database search where you are matching keywords or values exactly. If you search a normal database for dog, you will not find documents that say canine or puppy unless you specifically wrote code to handle those variations. If you search a vector database for dog, you will surface documents about puppies, breeds, veterinary care, and other related ideas because their embeddings are nearby in that number space. That is the fundamental difference. Similarity search instead of exact match. Why would you actually want that? The obvious follow-up question is, when does similarity search matter? And the honest answer is, in more places than you might think, but also fewer than the hype suggests. The clearest case is when you want to find things that are related to a query, even if they do not share the exact same words. Searching your own notes or documents is a good example. If you wrote a note 6 months ago about meeting planning, and you now search for calendar prep, a keyword search will probably miss it. A similarity search will likely find it, because the embeddings for meeting planning and calendar prep are close. Another strong case is retrieval augmented generation, which people usually call RAG. This is the technique where you feed relevant documents to a language model to help it answer a question with real context instead of just making things up from its training data. To do that, you need to quickly find the most relevant documents from a potentially large pile, and similarity search is exactly the right tool for that job. Two more use cases worth knowing. Beyond note search and RAG, there are two other use cases that come up often enough to mention. The first is deduplication. If you have a large database of records and you want to find items that are near duplicates, meaning similar but not identical, you can embed all of them and look for close neighbors. This catches things like the same product listed twice with slightly different descriptions, or customer records that almost match but have minor variations in how names were entered. The second is simple recommendations. If you embed all the items in a catalog, products, articles, videos, whatever, and a user interacts with one of them, you can find the nearest neighbors in the embedding space and suggest those. This is not the most sophisticated recommendation engine possible, but it is surprisingly effective for a relatively small implementation cost. And both of these use cases share the same property as Note Search and RAG. You care about meaning and relatedness, not just exact string matching. The honest question nobody asks out loud. Here is where I want to slow down and say something that tends to get buried in tutorials. The honest question is, do you even need a dedicated vector database at all? And for a lot of projects, the answer is no, at least not to start. If you have fewer than 100,000 vectors, or maybe even 1,000,000 at the smaller end, you can often get very good results with a simple library that runs entirely in memory or saves to a plain file. Tools like Face or ChromaDB or similar can run locally without any server, any cloud subscription, or any infrastructure. You load your embeddings into memory, run a search, and get results back in milliseconds. That is it. No database server to manage, no network round trips, no scaling configuration. For a personal project, a small team tool, or a prototype, this is almost always the right starting point. The heavy dedicated database layer is solving problems you do not have yet. When a dedicated database actually earns its place, that said, a dedicated vector database does earn its place once you hit certain conditions. The main one is scale. If you are storing tens of millions or hundreds of millions of vectors, you cannot just load all of them into RAM on one machine. You need a system that can shard and index them intelligently so you can still run fast queries without reading everything. The second condition is when you need real-time updates. If your corpus of documents is changing constantly, things being added and removed continuously, a simple in-memory index becomes painful to keep fresh. A dedicated system is built to handle incremental updates without you having to rebuild everything from scratch. The third condition is when you need the vector search to be one part of a larger query, combined with filters or metadata lookups. Some dedicated vector databases let you say, find the 10 most similar documents to this query, but only among documents tagged with this category and created in the last 30 days. That kind of hybrid query is awkward to build yourself on top of a flat file approach. Real failure modes, not theoretical ones. Now let me talk about where vector database setups actually go wrong in practice, because this part is usually skipped. The first and most common failure is weak embeddings. The similarity search is only as good as the model producing the embeddings. If you use a small general-purpose model and your content is highly specialized, like dense legal text or medical terminology, the embeddings may not capture the domain meaning well enough to return useful results. The fix is to either fine-tune an embedding model on your domain or use a stronger model from the start, which costs more per call. The second failure mode is a stale index. If your documents change but you do not re-embed and re-index them, your search results reflect the old state of the world. This sounds obvious, but it bites people often, especially when documents are updated in place rather than replaced. You need a pipeline that reliably re-embeds content when it changes, and that pipeline needs to be maintained. The third failure is scaling pain. People often start with a simple setup, it works fine at small scale, and then they just grow it without rethinking the architecture. Suddenly queries are slow, memory is exhausted, and the system that was a clean prototype is now a fragile production dependency. Plan your scaling path before you need it, not after. The hype is real, but so is the problem it solves. Even not be honest about the hype, because there is a lot of it. Vector databases got swept up in the broader AI wave of the last couple of years and marketed as magic infrastructure that every application needs. Some vendors in this space have done a very good job of making what is essentially a specialized index structure sound like a fundamental shift in computing. It is not that dramatic. The underlying math has been around for decades. The reason this suddenly became a product category is that large language models made it practical to generate high-quality embeddings cheaply and quickly, which made the use case of semantic search suddenly accessible to a lot more developers. That is a real and useful development. It does not mean you need to rebuild your entire data layer. The sensible framing is, if your application needs to find similar things in a large body of content, and exact keyword matching is not good enough, then you have a problem that vector search solves cleanly. If you do not have that problem, you do not need the solution. What to actually do with this information? So here is a practical way to think about this if you are building something. Start by asking whether your search problem is actually a semantic problem. Do users need to find content that is related in meaning even when the words do not match? If yes, embeddings and similarity search are the right direction, then ask how large your corpus is. If it is small, use a library that runs locally. Do not stand up a database server. Build the simplest possible thing first. Add the dedicated infrastructure only when the simple thing actually breaks under real load. And when you pick an embedding model, spend some time evaluating it on your actual domain content, not just on generic benchmarks. A model that scores well on general benchmarks may behave poorly on your specific content, and that mismatch will quietly degrade your results in ways that are hard to debug later. Shouldn't get your embeddings right first. The single most important investment you can make in a vector search system is in the quality of your embeddings, not in the database layer. A great embedding model with a simple flat file index will outperform a mediocre embedding model with an expensive dedicated database almost every time. The database is the infrastructure, the embedding is the signal. Signal quality is always more important than infrastructure sophistication at the scale most people are actually operating at. So if you have a budget to improve your system, and you are not yet at the scale where infrastructure is the bottleneck, spend that budget on a better embedding model first. Run real evaluations with real queries from real users. Look at the results and ask honestly whether the things coming back are actually what someone would want to find. That feedback loop is the work that makes vector search good, not the choice of which database server to run. The simple, honest summary. So here is the plain summary. An embedding turns text into a list of numbers that captures its meaning. A vector database stores those number lists and lets you search by similarity instead of exact keywords. That is useful when you need to find related content, power a RAG setup, deduplicate near matches, or build simple recommendations. You probably do not need a dedicated vector database until you are at significant scale or have specific requirements around real-time updates or hybrid queries. The real failure modes are weak embeddings, a stale index, and growing past your architecture before you rethink it. The hype is overblown, but the underlying problem it solves is real. Start simple, validate your embedding quality first, and only reach for the heavier infrastructure when the simpler thing actually breaks. If you found this useful and you want more honest, plain explainers on how AI tools and systems actually work, subscribe and follow along. Thanks for watching, and I will see you in the next one.